Okay, for a young chemistry student, or let me rephrase that, for a chemistry student that is new to chemistry, for an elementary chemistry student, what I'm about to do is not easy. It's a little bit difficult. But you know what? It's good because there's no memorization. It's very, very conceptual. Okay? Very conceptual. Now, carbon is unique on the planet in terms of what? Anybody want to gather a guess? Why carbon? Water is very unique, and carbon's very unique. Does anybody know why carbon is so intensely and incredibly unique? It does what? What is carbon in all of? That didn't sound very good, did it? That didn't sound well, did it? Okay? What is carbon? What is composed of carbon? Important thing. What is it? No.
All natural things.
Yeah, all natural things. What does that mean, natural? Like a rock is natural.
Raw material.
Raw material. What does that mean? You want me to help you out here? You guys? What is it? Life. Life on this planet. Living things are composed predominantly of carbon. Water, obviously. Hydrogen, oxygen, water. But also carbon. Matter of fact, if you go to college and major in biology or some kind of biology or chemistry, when you're a sophomore, second year, you will take something called organic chemistry. And organic chemistry is legendary in terms of its difficulty. People don't like organic chemistry. Those who like organic chemistry end up loving chemistry. So if you become a chem major, it's because you liked organic chemistry, not hated it. I quite liked it. I was a very odd person. I liked it. So we're going to be talking a little bit about organic chemistry today. All right? Now, let's look at the filling of carbon. You have 2s, okay? This is going to be, carbon is going to be helium, and then 2s2, right? And then 2p2. Are you with me? Yes, is that correct? The 2p will be higher or lower energy than the 2s? A little bit higher. Very good. This could be a little bit higher. Right? Yes? Now, according to this kind of short form electron filling diagram that I wrote on the board, how many bonds can form with carbon? Just looking at this, how many bonding opportunities does carbon have? Just what? How many places? Just 2, right? Here and here, right? In terms of covalent bonding and electron pairing and sharing, etc., do you see that only 2 places are available for electrons from another element to come in and bond? Do you see that? Yes? So in other words, if I had hydrogen and I had this, couldn't these form a bond? And if I had another hydrogen here, couldn't these form a bond? Yes? Is there any place else? Not really, is there? Right? So, but carbon forms a lot of different bonds. Carbon, one of carbon's hallmarks is that carbon forms 4 bonds. And the way it does that, tell me if I'm still on here, okay? The way it does it, it's something called hybridization. And what we're going to do when we talk about hybridization, we're going to talk about a very stable kind of arrangement of the S and the P's. In other words, the first kind we're going to talk about is sp3. In other words, these 4 orbitals go like this. like that. And they form 4 bonding sites. Now those bonding sites are all the same energy. And I kind of drew this incorrectly a little bit, so let me redraw it. They form a very nice stable state, kind of a hybrid state between what it was and what it is. Okay? Now, what happens is, I can now form what they call sigma bonds. 4 sigma bonds. You see, hydrogen can form 1 sigma bond. So I have hydrogen, and then I have carbon. There's my carbon and hydrogens. That's called methane. So that's big, right? Now I can form long chains of carbons. Soaps, protein, everything. I can draw enormous chains of carbons. There are enormous chains of carbons in proteins, in fats, in lipids, all kinds of things. So now I can form long chains of carbons. Every dash is a hydrogen bond, okay? This is 1, 2, 3, 4, 5, pentane. 2 would be ethane. 1 would be methane, ethane. Propane, you've heard of propane. Oh, yeah. Okay, this is propane. Butane, propane and butane, these, liquid petroleum gas, LPG. This is that's butane. Pentane, that's really LPG right there. Yeah? Okay. Octane, you've heard of octane in gasoline. Now we're getting into the liquids. Decane. Kerosene is another one. That's long chains, correct? Fats, lipids, correct? We're going to study those things when we talk about in the properties of water, etc. Okay, now, has anybody ever heard of something called a point of unsaturation? Polyunsaturates in oils and butter and things like that. This is margarine. Margarine is disgusting. Margarine is just enormous chains of carbons that go on forever, right? And what they do is they look like this. They're like this. This is what they look like. And you see how you can stack them? If you line them up, they'll stack. You see that? And so you can take oil and hydrogenate it, right? And then stack them all, and it forms this nice solid margarine. It's disgusting. Okay? What's an unsaturation point? Well, if I take this and I take out the hydrogen, I put in unsaturation points, it goes like this. You get these points of unsaturation. An unsaturation point is actually a double bond. So you get this. So you get only 1 hydrogen there, right? Because you get 1, 2, 3, 4. You see that? You see that? Yes? These are hydrogens, yeah. You get it? So each carbon has 1, 2, 3, 4. So you get these kinks. Olive oil, you have a lot of these double bonds. They're easily broken. Yes? We know what sp3 is. I explained that. You get the 4 bonds, right? These are all sp3s, where all the carbons have 4 bonds. Yes? So what's this double bond business? Well, double bonds are very important in eating a healthy diet. And they're easily digested. They're easily broken down. And I'm going to show you how. sp2. sp2 looks like this. right? Get it? This is what it looks like before. And then, am I on camera? Am I on camera? And then it goes to this. Some intermediate states. This is sp2, an S and two P's. And then you get this extra P over here, right? This is sp2, and this is an extra P, right? Because you can have 4 orbitals, right? Yes? This is a higher orbital. It's not as stable as these guys are. See how these are more stable? So what happens is this. So you get something like ethene, right? Okay, you get it? So let's look at one carbon. We're going to look at this carbon, right? And you have 1, 2, 3, 4 bonds, right? Yes? Okay. These here form sigma bonds. So these are, where's the top of this? These are sigma bonds. So you can form 3 sigma bonds. Here's carbon, here's hydrogen, here's hydrogen, am I on camera? Am I on? Okay. Am I on? How's that? Is that good? Now, so 1, 2, 3 bonds, right? You get that? These are the sigma bonds, right? Then you take this pi bond, this other p bond, and it goes like this. You get a p orbital. What's a p? What's the shape of a p orbital? Do you remember? Dumbbell shape, right? Very good. Haley's kind of drawing it. I like that. Kind of a dumbbell shape, right? Figure 8. So it looks like this. Right? Yes? So you have these other sigma bonds here. So you have these sigma bonds. 1, 2, 3, 4, 5 sigma bonds, right? Yes? Yes? So you have each carbon has 2, 4, 6 bonds, right? 6 electrons, right? But then you get these sigma bonds. You get this leftover P, right? It looks like this, right? Yes? And what they do is they overlap. Yes? This green, this forms a pi bond. You get this overlapping. This is a weak bond. This pi bond is weak. You see how it's a higher energy? So it's a little weak. And that's exactly what happens. Yes? That's a hybridization. You get it or what? Now, in a triple bond, how many pi bonds would you have? 3. No. In a triple bond, look up, do they have sp hybridization? We did sp3, yes? Methane, etc. Alkanes, right? sp2 is when you get this business here. What about sp3? Okay. You have it? Is it in the book? Yeah. What does it say about it? Okay. But how many P bonds are there?
3 P bonds and 1 S bond.
No.
4. Wait.
No. Let's do sp hybridization. Okay? What is it? That's right, there you go. Let's look at sp hybridization. This is all in the book. This is all on my video, all on the lecture video. Okay? So if I have this again, let's do this again. Right? Is that on the camera? Okay. So this becomes, let's do this again. This is higher energy. You know what? Let's move this over. just move this over. So this becomes some hybrid, right? There's an S and a P, and then I have these two left over, right? These are P's, correct? Higher order P's, yes? Okay, so you get this. You get this. You get it? This is a triple bond. This is this compound. Acetylene. Acetylene for welding. Acetylene. Okay? That's the sigma. So you get 2 sigmas. You see that? 2 sigma bonds? You see that? Because you have, there's the sigma bonds right there. Now you have 2 pi bonds. Let me make this a little bit clearer. I don't know where all my markers have gone. Let me put the C's. Okay, I'm kind of putting them a little bit at angles away from each other. They're not going to be straight across necessarily, but let's make it straight across. Okay. You can see my art is just impeccable. I have a showing at the Louvre this coming weekend. Okay, so I have, let me just do this. Okay, and then I'll put in green. Right, are we good? Is that good? Yes? Sigma bonds, 3 sigma bonds, right? Are we all right with that? 3 sigma bonds. There's 1 here, okay? There's 1 here for each carbon, right? There's 2, and then, right? Get it? Yes? Yes? Okay. And then we have 2 pi bonds left over, right? I can't draw for beans here. Okay, so you get this 2 pi bonds. It's kind of hard to see it, yeah. It's kind of hard to draw this, but you get two pi bonds. So these are pi bonds. This is a pi bond. This is sigma. This is sigma. And this is sigma. Is that right? You get that? Sigma, 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 and then pi and pi. You get that?
So there's 3 sigma bonds and 2.
All together.
Yeah, all together.
The triple bond is going to be
1 sigma. No, 2 pi, 1 sigma bond.
That's right. That's right. That's right. You always have 1 sigma bond. Then the other 2 are pi bonds. Haley, are we there? Is that about what was said there? Did I complete it pretty well?
Yeah.
Yeah. You get it? You get it?
Yeah.
It's actually kind of, I mean, can you imagine that there are people that find this really hard? It's not hard, is it? It's pretty good? Yes? Yeah? So it's just a little wild that, you have this, the hybridization, this is the hybridization. Let's go through that once more. Hybridization, if I can put it in kind of like You know, street lingo, kind of informal, Darcy kind of. It's just, you're just taking orbitals of different energies. See, it's hard to take orbitals of different energies and make clear bonds with them. If you make them all the same energy, then the molecule is much more stable. You get it? Much more stable. Because what you get is you get this lower energy. Yes? You get this low, oh, it's on. That's pretty cool. All right, so you get this lower energy, and you get 4 nice bonds. You know, otherwise, can you imagine building a wooden box where all the different pieces of wood are different? Some of the studs that you're using to make the box are oak. Some of them are pine, maybe poplar, right? Maybe balsa wood, different densities. Maple. Maple's actually a pretty strong wood, but fair enough. So you have really strong wood like maple and oak, which is very strong. What's the difference between oak and maple? This is oak. I'm sorry, this is oak, right? Oak, maple looks like this. It's just overlapping, so it's stronger, really, in a sense. It's a little stronger, but anyway. And then you have what used to be made of, what still is made of ash? Very good, baseball bats. Okay. I grew up when I was a kid playing ball. We never had metal bats. Metal bats were new after I like a good wooden bat. But anyway, so can you imagine making a box out of wood that's all different densities? Would that be a strong box? It'd be a little goofy, wouldn't it? So this says, well, let's make the box out of all the same wood. Isn't it going to be more stable? We'll make it all oak, all low energy. And it's going to be much more stable. And that's what hybridization is. Life is very stable. Can you imagine this weak little shell of a thing being able to live? My mother is 98, she'll be 99. The doctors, my sister just sent me an email, she's so healthy, the doctors believe that she'll live over 100. Can you imagine? It's unbelievable. And all of these molecules have tons of these hybridized bonds. So the molecular orbital theory is very important. This is the molecular orbital theory in one sentence or less. The conversion of S and P sub energy levels that contain orbitals into individual hybridized orbitals which have all the same energy. That's it. I'm not repeating myself because it's on energy. As a result, sigma and pi bonds can be formed. The formation of 4 sigma bonds from sp3 is the best because pi bonds are unstable. What's a very good example where you have a substance where pi bonds are very unstable? In terms of naturally occurring gases, the most powerful, the most flammable, the most energetic gas known on Earth. It's not there. It's about to turn to it. Is this. Acetylene. 2 pi bonds, very unstable. Yes? But they can form. Sometimes it's not so much that a pi bond is unstable. That's not the issue. So why form a bond, right? Is that what you're saying? Well, it's not so much that a pi bond is unstable, so we're going to poo-poo it. But the fact that the presence of a pi bond in sp and sp2 hybridization allows you, Haley, you're drifting, right? I can tell by your smile you knew you were drifting. That it allows you to form a diverse number of molecules which allows for the diversity of compounds. What is evidence that we have a diverse number of carbon compounds. What's evidence that we have a diverse number of carbon compounds? You know what the number one evidence? You looking at me and saying, whoa, Darcy is a weirdo, man, I'm telling you. Darcy is full of all of these diverse forms of carbon-carbon bonds that contain pi bonds and some kind of hybridization. Look, guys, methane is big in the human body. I'm sorry, it's big. You know, it's produced in the colon, gas, body gas. You know, we use the F word when somebody has body gas. You produce methane. And yes, those things are flammable. Methane. And methane is an odorless, colorless gas. But when you mix methane with byproducts of metabolism, especially where sulfur is involved, you get you get smelly gases. Okay? But that's because you get this metabolism or partial metabolism of certain things like starches. Starches, if they're not digested properly, if you eat too fast, you get this putrefaction of carbohydrates. And that putrefaction of carbohydrates leads to yeast infections in the colon. Colon can have yeast infections. It's called candida. So all of a sudden, this production of methane, which is 4 sigma bonds, 4 sigma bonds, very common in the digestion of foods. One of the problems on the planet is that you know that, what is a greenhouse gas? Name me one. Yeah, the common one, CO2, right? Carbon dioxide. Dangerous greenhouse gas. Do you know what's 25 times more dangerous than carbon dioxide? I mean, that's big, right? 25 times. Can you imagine if you were 25 times taller than you are now? Like you're 6 feet. You'd be like 150 feet, right? Okay, can you imagine? Trying to go down to the mall and get some shoes? Very difficult. Okay, but this methane is 25 times more powerful than carbon dioxide. 25 times worse, however you want to put it. 25 times more effective in the reflection of those longer waves back. Shall I give you a quick review of this? The sun comes in, the sunlight comes in, short wavelengths. It's soaked up by things, by like roads, us. Things soak up the rays, yes or no? Yes or no? And then I should have used blue. Shall I do that over? I'm being a little obsessive compulsive, my apologies. So we'll use green here. Okay, this is far too disproportionate. But the short waves come in, blue. The terrestrial things, rocks, organisms, sand, the earth, darkness, whatever, absorbs these things, right? And what does it do? It heats them, right? And the heat is re-radiated. Well, heat is longer wavelengths. These are short wavelengths. These are longer. The longer wavelengths can't get out. And it goes back. See there? They bounce. What causes them to bounce back? Carbon dioxide, right? What's 25 times more effective at causing that reflection of the longer wavelengths back into the planet, causing greenhouse effect? Methane and cows, livestock, producing all of that methane gas. The methane gas that's trapped in the tundra in the frozen north, that's thawing, it's going to release methane, decaying organic matter. Not just what's decaying inside your intestines, but what's decaying in the northern latitudes. Livestock to feed the planet. The consumption of beef could be Some argue that the consumption of beef is going to be the downfall of humankind. It's a little bit crazy. But you're producing this, and you have 4 sigma bonds. Enough? Enough? Hybridization, do you get it? We're done.